4차 산업혁명 13주 3차 시강의를 시작하겠습니다. 챕터 15는 지구공학입니다. 이번 시간은 기후변화의 해결로서 뉴클리어 퓨전이 가능한지에 대해서 알아보도록 하겠습니다. 관련 동영상을 보면서 설명하도록 하겠습니다.
Think of nuclear power, and many imagine the worst. Atomic bombs, reactors melting down, radioactive wastes. There's no denying that the history of nuclear is fraught, and the dramatic and disturbing moments hard to forget.
뉴클리어 하면 부정적인 역사가 많고 후쿠시마처럼 잊기 힘든 순간들이 있습니다.
But for the most part, nuclear energy operates out of sight and out of mind, generating about 10% of the world's total electricity. This represents 29% of all the world's low-carbon power, and 55% of the United States' low-carbon power.
뉴클리어는 현재 전 세계 에너지의 10%를 생산하고 있고 저탄소 전기의 29%를 생산하고 있습니다. 미국에서는 55%나 됩니다.
Nuclear reactors generate energy day and night and produce no greenhouse gases.
원자로의 강점은 그린하우스 가스를 생산하지 않으면서 낮과 밤 언제나 생산할 수 있다는 점입니다.
But overall, the growth of nuclear is slowing in comparison to other low-carbon sources like wind and solar.
By 2050, all 420 nuclear plants operating today must be replaced.
2050년까지는 420개의 핵 발전소들이 교체되어야 합니다.
We're not on a path to get there.
Nuclear power plants are expensive to build, construction often takes longer than expected, and debates over how to handle radioactive wastes rage on. What's more, public opposition to nuclear power is strong, especially in the US.
핵발전소는 짓는데 시간이 오래 걸리고 웨이스트 문제도 있고 여론도 좋지 않습니다.
But we're in the midst of a climate crisis, and many energy experts argue that despite a contentious history, nuclear has a key role to play in our energy future as a stable, always available source of power.
우리는 현재 기후에서 위기를 맞고 있고 에너지 전문가들은 뉴클리어가 중요한 역할을 해야 된다고 말합니다.
As we replace coal, we really do need another form of what we call spinning reserve. Large power plants that when the wind isn't blowing or the sun isn't shining.
올해는 석탄 사용을 줄이면서 바람이 불지 않고 해가 없을 때 사용할 수 있는 큰 에너지 플랜트를 필요로 합니다.
That power is available, and nuclear is going to be the best solution for that.
뉴클리어는 그것을 위한 최선의 선택입니다.
If you just believe in arithmetic, you need nuclear.
여러분이 산수를 믿는다면 뉴클리어를 필요로 합니다.
Some experts are working to upgrade existing nuclear power technology. That means designing safer and more efficient fission reactors with the support of philanthropists like Bill Gates. But government labs, private investors, and intergovernmental organizations are also devoting vast resources to what many consider the holy grail of energy, nuclear fusion.
더 안전한 뉴클리어 발전소에 많은 연구가 진행되고 있고 뉴클리어 퓨전에 많은 리소스가 투입되고 있습니다.
Good grief. The energy potential there is just enormous. The energy that we need is going to be mastering this fusion.
Nuclear fusion is the same process that powers our sun and every other star in the universe. And if we can figure out how to harness that power here on Earth, it would be a huge game changer.
뉴클리어 퓨전이 현실화된다면 에너지 산업에 일대 변혁이 일어나는 게임 체인저가 될 것입니다.
Nuclear fission was discovered in late 1938 by a pair of German researchers. They found out that when you bombard uranium with neutrons, the nucleus splits, forming two lighter isotopes and releasing mass that gets converted into energy. The discovery paved the way for the development of the atomic bomb in the United States. And after the infamous bombings of Hiroshima and Nagasaki, concerns over nuclear proliferation spiraled as the global nuclear stockpile grew during the Cold War between the United States and the Soviet Union. But in 1953, President Eisenhower's Atoms for Peace program attempted to shift the focus of nuclear power toward peaceful energy generation, and much of the world started building nuclear power plants for civilian use.
뉴클리어가 처음에는 핵폭탄으로 제조가 되었지만 나중에는 민간 사용으로 전환되었습니다.
Private industry quickly jumped on board, especially in the United States. And by 1991, the U.S. had twice as many operating nuclear power plants as any other country.
If those all of a sudden went away and you had to make that electricity with fossil fuel, it would be like doubling the number of cars on the road. So our 100 nuclear power plants in the U.S. are helping us avoid, and have been for like 50 years, helping us avoid a significant amount of carbon generation.
핵 발전소는 카본 제너레이션을 줄이는데 크게 기여하고 있습니다.
As of 2019, about 450 reactors worldwide operate in 31 countries. And some countries, such as France, Hungary, Slovakia, and Ukraine, get more than half of their power from nuclear energy.
전 세계에는 450개의 원자력 발전소가 있는데 프랑스는 72%를 원자력에 의존하고 있습니다.
But over the decades, a number of high-profile disasters have stalled the industry's momentum. In 1979, the partial meltdown and ensuing radiation leak at 3 Mile Island in Pennsylvania cost about $1 billion to clean up. The disaster stoked public fears about nuclear power. Stricter safety standards were imposed. Reactors became more expensive to build, and fewer were built.
원자력 발전소에서 사고가 발생하면서 안전 우려가 커졌고 가격이 상승했으며 더 적게 짓게 됐습니다.
Fission is always also quite expensive, and because of the large amount of radioactivity in those machines, people are scared of it, so the social acceptance of fission is not very good.
The nuclear disasters at Chernobyl in 1986 and Fukushima Daiichi in 2011 led to further scrutiny of the industry, as concerns mounted over the long-term effects of the radiation exposure.
뉴클리어는 웨이스트를 어디에 저장하느냐가 큰 문제입니다.
And then there's the battle over where to store nuclear waste. One proposed site, Yucca Mountain in Nevada, has been hotly contested for over 30 years.
Yucca Mountain is unfit as a repository site for nuclear waste because of the impact it would have on national transportation.
The current state of the industry remains mixed. Countries such as China, India, and Russia are building new reactors at a fairly fast clip. But in the United States, more than 1/3 remain unprofitable or face closure.
Frankly, we're rusty. If you look at countries like China and Russia, we're being outnumbered by 30-1 on new builds.
러시아와 중국에 비해서 미국은 새로 짓는 원자력 발전소가 30대 1에 불과합니다.
Only one new nuclear reactor has come online in the U.S. since 1996, as costs and construction times in developed economies have spiraled.
The typical nuclear plant today in Europe costs well over $10 billion and generally takes 10 years to build.
원자력 발전소를 짓는 데는 1조 원이 넘고 기간은 10년이 걸립니다.
The low cost of solar, wind, and in particular natural gas has meant that nuclear not only comes in at a very expensive proposition, but it also means that nuclear is not a very friendly player in the market.
Next-generation fission technologies are much safer than reactors of the past, and some proponents claim they'll be cheaper too.
차세대 뉴클리어는 훨씬 안전하고 가격도 낮다고 주장을 합니다.
The general public may still need convincing, but one idea has outlasted the controversy: the promise that someday nuclear fusion will provide a better alternative.
뉴클리어 퓨전은 실험만 될 수 있다면 더 나은 대안이 될 수 있습니다.
Scientists have been researching nuclear fusion since the 1920s, ever since they learned it's what powers the sun. In a fusion reaction, extreme temperatures and intense pressure cause hydrogen atoms to fuse together, forming helium atoms. In the process, the atoms lose some mass, which is converted into vast amounts of energy. The reaction could produce 4 times as much energy as nuclear fission, and nearly 4 million times more energy than burning coal or gas.
뉴클리어 퓨전은 핵 분열보다 4배의 에너지를 만들 수 있고 콜이나 가스보다 400만 배의 에너지를 만들 수 있습니다.
Fuel is plentiful and can be found essentially everywhere in the world. The radioactivity would be short-lived. There's no possibility of a runaway reaction, so it's an inherently safe system.
But after decades of research and billions of dollars, scientists still have not found a way to create a sustained fusion reaction. That's created a not-so-inside joke among scientists. that fusion is the energy source of the future and always will be.
많은 투자에도 불구하고 뉴클리어 퓨전은 원하는 결과를 내지 못했습니다.
But some think these questions and jokes overlook the real progress that's been made.
Although we don't have fusion, over the last 30, 40 years, the amount of fusion that the prototype make have increased by a factor of 10 to the 4, 10,000 times.
과거에 비해서 프로토타입이 만드는 퓨전은 만 배나 증가했습니다.
And this is actually a growth rate similar to the amount of transistor on a chip.
The challenge is until you get to the point where you build that first power plant, everybody thinks you haven't moved very far.
우리가 첫 번째 퓨전 파워 플랜트를 만들기 전까진 인정을 받기가 쉽지 않을 것입니다.
Fusion has traditionally been the purview of government labs like Lawrence Livermore and Oak Ridge. But more recently, a number of private companies have thrown their hat in the ring. This includes General Fusion, which aims to bring a commercial reactor to market in the 2030s. Amazon CEO Jeff Bezos is among the company's investors.
과거에는 뉴클리어 퓨전 연구가 정부에 의해서 이루어졌지만 현재는 아마존의 제프 베조스와 마이크로소프트가 크게 베팅하고 있습니다.
And then there's the large multinational effort that's underway in the south of France. Called the International Thermonuclear Experimental Reactor, or ITER, the project aims to create the world's largest and most powerful fusion reactor.
이터는 현재 가장 강력한 퓨전 리액터를 건설하고 있습니다.
While all of these players are competing for resources and funding, that could actually be a good thing for the nuclear power industry overall.
The success of one company or one group or one organization actually grows the pie. It convinces more people out in business and in the economy to look at fusion as a viable alternative, and that attracts more investment for everybody.
이러한 현상은 인더스트리 전체 파이를 크게 하기 때문에 반가운 일입니다.
General Fusion, founded in 2002, operates out of a nondescript office park about 20 minutes outside of Vancouver. Unlike most government labs or academic institutions, General Fusion is focused on implementation over research. The company's goal is to build an electricity-generating fusion reactor in the next decade or two.
이 회사의 목표는 10년에서 20년 사이에 전기를 발생시킬 수 있는 퓨전 리액터를 만드는 것입니다.
Jeff Bezos was an early investor, and the company has now raised over $120 million, with about $90 million coming from private investment and $30 million from the Canadian government. General Fusion combines two common approaches in the industry: inertial confinement, which subjects the fusion fuel to extremely high pressure for a brief amount of time, and magnetic confinement, which uses modest pressure for a prolonged time.
이 회사는 퓨전 연료를 짧은 시간 동안 강한 압력의 이너셜 컨파인먼트 방식과 긴 시간 동안 중간 수준 압력의 마그네틱 컨파인먼트 방식을 결합합니다.
When heated to extreme temperatures, the fusion fuel becomes a plasma.
아주 높은 온도에서 퓨전 퓨얼은 플라즈마가 됩니다.
A state of matter similar to gas, except that it contains charged particles that allow it to conduct electricity and respond to magnetic fields.
플라즈마는 가스와 비슷하지만 차지 파티클을 갖고 있어서 전기를 통하고 자기장에도 반응을 합니다.
Our compressor is going to be a big sphere, about 4 meters across, 15 feet across on the inside. And into that big sphere, we are going to put liquid metal. And that liquid metal, we're going to spin around in a circle so it opens a hole. And into that hole, we're going to put our fuel, which is hydrogen gas. It's preheated up to a few million degrees. And then all around the outside of this sphere is a big array of pistons driven by compressed gas. So they push on the liquid metal and they collapse the hole with this fuel trapped inside. And that collapse happens very quickly and compresses the fuel up to fusion condition.
외부의 장비들은 플라즈마에서 퓨전이 일어나도록 컴프레싱하는 역할을 합니다.
The peak of the compression, the fuel ignites and gives a fusion reaction. That energy goes into this liquid metal.
퓨전이 일어나면 그 에너지가 메탈로 전달이 됩니다.
So the liquid metal heats up. You take this hot liquid metal out, you run it through a heat exchanger and you boil water and make steam. And the steam drives a turbine to make electricity.
히트는 스팀을 만들고 그것이 터바인을 움직여서 전기를 만들도록 합니다.
Puts it out on the grid. And we just keep pulsing and do that over and over again.
Right now, General Fusion's main components, like its plasma injector, piston array, and fuel chamber, all exist separately. Delage wants to integrate them into one large demonstration reactor, a process he estimates will take about 5 years.
현재 분리된 요소들을 5년 뒤에는 모두 인테그레이션하는 것을 목표로 하고 있습니다.
A space roughly this size would fit a power plant that would be enough for 100,000 homes.
And when the reactor goes online, LaBerge says it will bring General Fusion's cost of power into competition with coal and renewables like wind and solar.
뉴클리어 퓨전이 윈드와 솔라에 비교해서도 가격 경쟁력이 있도록 하는 것이 목표입니다.
At 5 cents per kilowatt hour is quite competitive actually, it's cheaper than many other things, but it's not cheaper than natural gas.
LaBerge hopes it will eventually become cheaper though, a likelihood if the US decides to implement a carbon tax.
The energy market on the planet is $1 trillion a year.
에너지 마켓 시장은 트릴리언 달러 정도입니다. 1,000조 원이 넘는 돈입니다.
And so if we take a sizable chunk of that, we get a sizable fraction of $1 trillion a year.
But some industry experts believe that private companies like General Fusion are being overly optimistic with their timelines.
In the past 10 years, there's been a lot of small industries coming in to say we can achieve fusion in 5 years, 10 years. I don't believe it. I think they've underestimated and not looked at the full challenge of a fusion reactor.
어떤 전문가는 제너럴 퓨전의 이러한 전망이 너무 낙관적이라고 생각합니다.
Nuclear fusion is hard. No research group or company has ever been able to reach the so-called break-even point, at which the energy released from a fusion reaction is greater than the energy required to heat the plasma used in the reaction.
It is basic research. Basic research has value, but to sell this as a technology that will solve our energy needs in the next 20 to 30 years is deceptive. We are just not that close.
이분의 생각에 뉴클리어 퓨전은 아직 베이직 리서치 단계이고 20-30년 안에 이 문제를 푼다는 것은 사실일 수 없다고 이야기합니다.
But basic research is the bread and butter of Lawrence Livermore National Lab. It's been researching fusion since its establishment in the 1950s. In 2009, the lab opened the National Ignition Facility with the goal of achieving break-even and ultimately igniting a fusion reaction.
베이직 리서치는 로렌스 리버머 랩이 가장 앞서 있고 퓨전 리액션을 이그나이트하는 것을 목표로 하고 있습니다.
And by ignited, we mean that it can be self-sustaining. It can propagate throughout all the fuel that's present in the implosion.
이그나이팅은 연료가 다 소모될 때까지 자기 유지를 한다는 뜻입니다.
Lawrence Livermore is pursuing inertial confinement fusion.
로렌스 리버머 연구소는 이너셜 컨파인먼트 퓨전을 사용하고 있습니다.
That is, confining plasma at extremely high pressure for a very short amount of time, using high-energy lasers to do so.
이너셜 컨파인먼트 퓨전을 위해서 하이 에너지 레이저를 사용합니다.
We're standing in what we call our target bay, looking at our target chamber. The target chamber is a big ball about 30 feet across, and at the very center of that ball, we put a very tiny target about the size of the tip of my finger.
뉴클리어 퓨전에는 타겟 볼이 있고 그 중심에는 손끝만큼 작은 타겟이 있습니다.
And we irradiate that target with 192 of the world's most energetic lasers.
그 타겟을 레이저로 비춤으로써 퓨전을 위한 이그니션이 일어납니다.
Researchers at the National Ignition Facility and other national labs have access to enormous computing power, allowing them to run complex simulations that help them understand the exact conditions necessary to reach ignition.
이그니션에 필요한 조건을 알기 위해서 슈퍼컴퓨터의 시뮬레이션을 사용합니다.
But clearly, getting everything to work perfectly in the real world is much harder than it looks on a screen.
The National Ignition Facility was based upon the promise of just that, ignition.
그들의 연구소는 이그니션 아이디어에 기초한 것입니다. 10년간 시도했지만 목표에 가까워지지 못했습니다.
They haven't gotten anywhere close. And when they fail, they say, all we need is a little bit more money and time. And the critics are saying, no, there's some fundamental problems here.
So it could very well be that neither the well-funded, research-oriented national labs nor the scrappy, goal-oriented startups are going to solve the fusion puzzle. It might just take an international effort.
뉴클리어 퓨전을 연구 개발하는 세 개 그룹입니다. 첫 번째로 스타트업인 제너럴 퓨전이 있습니다. 두 번째로 기초연구가 뛰어난 로렌스 리버머 랩이 있습니다. 세 번째로 국제적 협력과 공조가 이루어진 이틀 프로젝트가 있습니다.
Device should be completed around the 2024 period, and then targeting to go nuclear in the 2035 period. So by 2040, which seems a long way, we will have gained all the information that allows the next generations to build demos.
이틀 프로젝트의 목표는 2024년까지 디바이스를 만들고 2035년에는 뉴클리어 퓨전을 시작하는 것입니다. 2040년까지는 충분한 데이터를 모아서 다음 뉴클리어 퓨전을 위한 준비를 합니다. 그들은 이 프로젝트를 통해서 이그니션을 할 수 있기를 희망하고 있고, 그렇게 되면 산업용 리액터를 통해서 전기를 생산할 수 있습니다. 어펜딕스입니다. 지금까지 시청하신 것으로 이번 차스의 수업이 인정됩니다. 관련된 동영상을 계속 보도록 하겠습니다.
Not everyone thinks fusion is so integral to our survival.
Fusion isn't the only game out there. Fission is like fusion's ugly sibling. It's like no one wants to get involved with it. But that is the only technology that we have outside of solar and other sorts of renewables that we can produce energy without carbon waste.
Public opinion on nuclear fission remains split, but many within the industry say the controversy is undeserved.
It's controversial for those who haven't studied it carefully. For those who have studied it carefully, it's not. You look at the mortality rates per unit of energy produced, and nuclear is the lowest of all. But there is a fear because of its origins.
Many proponents of nuclear say to look back at the past, to the accidents that happened, is being naive about the innovation and evolution of technologies.
Microsoft's Bill Gates is one of these proponents. He's intent on building safer and more efficient fission reactors to reinvigorate the industry. In 2006, he founded TerraPower, a nuclear reactor design company that's working on building new Generation 4 reactors.
Most of the operating reactors around the world today, of which there's about 450, are Generation 2. Generation 3 plants are now being built out in the US, in China, in Russia. Generation 4 plants, they represent improvements in not just economics, but safety and waste reduction. So the reactors that we're working on, they operate not just at lower pressures, which should be less expensive than today's reactors, but they operate at higher temperatures. When you move to those higher temperatures, you actually get a higher plant efficiency.
Levesque also says TerraPower's reactors are walk-away safe. That means that during emergencies, the plant will cool and stabilize itself without an operator present. Furthermore, Levesque says the plant produces 80% less waste and requires less uranium enrichment, allaying proliferation concerns. But getting new fission technologies off the ground is an expensive endeavor. So companies like TerraPower want government support, both to build out their tech and to help them compete with cheaper power sources, such as natural gas.
The US government does this all the time. They did it in the case of hydraulic fracturing, they did it in the case of wind and solar, and now it's time for the US government to help demonstrate the next phase of nuclear technology as well.
Levesque estimates that building TerraPower's first demonstration reactor will cost more than $1 billion, ideally funded through a public-private partnership.
I can't have my grandchildren, let alone my children, rely on fusion. This is something we've got to do because it's the one major system that we know we can build. It's a matter of how perfect we can make it, not whether it'll work.
So here's where we stand. Fission proponents want to upgrade existing nuclear power plants and technologies. Fusion researchers say projects like General Fusion and ITER need more investment from both public and private sources in order to turn nuclear fusion into a reality. And climate change activists say the world needs to decarbonize using the resources we have now, before it's too late.
We need to turn to fission turn to solar, turn to wind, turn to geothermal, turn to hydroelectric, do whatever we can to get off of the carbon addiction.
Then, if the research and investment comes to bear, we can turn to fusion to support our rapidly growing population.
I think fusion is actually an inevitable thing. I think we will solve this problem. The key is to get it there as fast as possible.
How soon we'll reach this fusion-powered future remains up for debate.
The first demonstration will happen in about 10 years, I would think.
By 2060 or 2070, the world is likely to be largely powered by fusion.
Near the turn of the century, or maybe even a little bit beyond that.
I think if the human race is still around in the year 2500 and we look back, I would wager that fusion plants will be there.
However, these estimated timeframes may rely heavily on how much government decides to invest in fusion power.
I think the question is political will. To what extent are our governments willing to spend the money to investigate these things? At this present rate and at this present level of will, I don't see it happening.
If you were to ask me what is the most challenging thing about fusion, I would not say holding some hot gas at 150 million degrees Celsius. I actually think it's our mentality. We don't think 5, 7, 12 generations down the road.
A more realistic plan and a portfolio is probably to concentrate on various renewables and work on improving standard fission.
Where there's a will, there's a way. And through the process of building a machine like ITER, as well as building a machine like NIFS, as well as building a machine like General Fusion, we learn so that we can then apply that to the next time. Yeah, it goes beyond our generation.